Welcome to this lesson. In this lesson, we'll be treating liquids. So we'll be treating specifically properties of liquid that are volume and vapor pressure rather, and boiling points. So let's hop into the lesson. So liquid possess, from when we're treating matter and different states of matter, we said that we have three states of matter: solid, liquid, and gaseous phase of matter. So we are specifically treating liquid and seeing how parameters of liquid that tries to distinguish liquid from solid, how they are important, some important parameters that distinguish liquids from other states of matter. So now liquids possess unique physical properties that distinguish them from solids and gases. So among these properties, we have vapor pressure and boiling points. So these two parameters are very, very, very important, and they help to distinguish liquids from other states of matter. So they are critical in understanding the behavior of liquids under various thermal conditions. So these two parameters are mostly applicable when we are dealing with temperature changes. So these properties also influence many industrial and laboratory processes. So let's see the first one: vapor pressure and molecular escape. So vapor pressure is related to molecular escape. That's why the title is that. So vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid at given pressure. So I remember when I said we move from liquid to gaseous phase, it's called vaporization or evaporation. So usually is in water that we call it evaporation, but generally it's called vaporization. So when we have liquids that are trying to move to gases, and those gases are also about to move to liquid phase, that state of equilibrium, there is a pressure that exists at that phase. So that phase of equilibrium is what is known as the vapor pressure. The pressure at that phase of equilibrium, rather, is what is known as the vapor pressure. So vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. That is, a vapor is in equilibrium with its liquid, or the liquid is in equilibrium with the vapor. So the pressure at that point, the pressure that vapor exerts on its liquid is what is known as the vapor pressure. The pressure that the vapor exerts on its liquid is what is known as the vapor pressure. So it's usually at a specific temperature, and it reflects the tendency of molecules to escape from liquid phase into vapor phases. So before a molecule vaporizes, it needs to attain some amount of energy or kinetic energy. The molecules of the liquid needs to attain some amount of kinetic energy, and once they've gotten that amount of kinetic energy, they can break from liquid phase into gaseous phases. So as they are about to break, there is this pressure that the gaseous phases are also exerting on them, trying to keep them in their vapor phase. So this vapor pressure that they apply is known as this pressure that the vapor or the gaseous phases apply on the liquid surface is known as the vapor pressure. So, and this vapor pressure, it's crucial. It's very crucial that we know this vapor pressure, because it helps to tell when liquids will be converted from liquid phases to vapor phases. So as temperature increases rather, more molecules gain sufficient energy to vaporize, resulting to high vapor pressure or higher vapor pressure. So let's see the boiling point. We've talked about vapor pressure, now we're going into boiling point. The boiling point of a liquid is defined as the temperature at which its vapor pressure equals to the external atmospheric pressure. So now there is a thing, like we mentioned vapor pressure, and we said vapor pressure is between the liquid and the vapor, or liquid and its vapor. So for boiling point now, we are dealing with when it's the boiling point of a liquid is dealing with when the temperature of sorry about that. The boiling point of liquid is defined as the temperature at which its vapor pressure equals to the atmospheric pressure. So when we've known vapor pressure already of a particular liquid, the point at which that vapor pressure becomes equal to the atmospheric pressure, that is surrounding pressure in the atmosphere, that point the temperature at that point is called the boiling temperature, or the boiling point of the liquid. So whenever the vapor pressure of a liquid becomes equal to the atmospheric pressure, that point is going to the liquid. When you reach that point, you've gotten to the boiling point of a particular liquid. So at this point, bubbles of vapor form between the liquids and rise to the surface. So when the vapor pressure of the liquid is equal to the atmospheric pressure from the atmosphere, boiling happens. When this kind of thing happens, and liquids begin to form bubbles which rise to their top and try to escape from the surface of the liquid. So the normal boiling point is can be defined as the temperature at which 1 atmosphere, at which the temperature of the vapor pressure is equal to 1 atmosphere. So the atmospheric pressure is assumed to be 1 atmosphere. So when the temperature of the liquid is equal, the temperature at which the pressure of liquid is equal to 1 atmosphere. Guess what I'm trying to say? We're talking about two pressures now. Atmospheric pressure, 1 atmosphere. So vapor pressure from the liquid. So when the vapor pressure is equal to 1 atmosphere, that temperature at that point is called the boiling point or normal boiling point of a liquid. So now we have different liquids have different vapor pressures and boiling points. So when you see water, it has its own vapor pressure and also has its own boiling point. Ethanol has its own boiling point and also has its own vapor pressure. And the reason for this variation is due to the different intermolecular force of attraction. So when the force of attraction between a particular liquid, the intermolecular force of attraction between liquids is high, this liquid would have high boiling points. So when the attraction between the molecules of liquid, that's when the particles inside the liquid, they hold themselves strongly. This liquid would find it difficult to boil. That is, the molecules of this liquid will find it difficult to escape from that liquid because they are already held together strongly. So the more strongly they are being held, the more difficult it is for them to escape into gaseous phase. That's to make it difficult. You need more energy and high temperature increase for you to be able to force them to leave that their zone. So that's how intermolecular force of attraction relates with the boiling points of liquid. And also this thing also applies to vapor pressure. So once this intermolecular force of attraction is high, it implies that the vapor pressure of the liquid is low. That's the liquids would barely want to leave the surface. So vapor pressure is the force that the liquid is trying to use to escape into gaseous phase or vapor phase. So because of they are holding themselves strongly, it means that their pressure, their direction of force is not outward, it's usually inward to themselves. So conversely, substances with weak attraction vaporize more easily. So substances that has weak molecular force of attraction or intermolecular force of attraction, they tend to vaporize quickly. Substances like alcohol, which vaporize even by exposure to just the air. So now, changes in atmospheric pressure affects the boiling points of liquid. So remember I was talking about boiling points of liquid, and I said before a liquid will boil, its pressure, the vapor pressure has to be equal to the atmospheric pressure before a liquid will boil. So when the atmospheric pressure is changing continuously, it affects the boiling point. So if the atmospheric pressure reduces, it means that the liquid's boiling point would become low. That is, the temperature at which the liquid will boil will become low because now there is less energy for the liquid to use to go out from its environment, from the liquid phase. So at high altitudes, where atmospheric pressure is low, liquid boils at a lower temperature, which is what I was just trying to say, that as the atmospheric pressure is reducing, it means less energy is required, meaning low temperature would cause liquids to boil. So this principle is used in vacuum distillation and other applications where boiling point manipulation is essential. So for cases where if you want to make something boil faster, reduce the atmospheric pressure. So this is the principle that's actually even used in stuff like pressure cooker. So when you reduce the atmospheric pressure of a particular liquid, the liquid will tend to boil faster than normal. It will boil less than 100 degrees centigrade. So understanding vapor pressure and boiling point is crucial for tasks such as selecting solvents, designing distillation procedures, and predicting evaporation rates. So these properties are also important in food processing and perfumery, and also in environmental studies. So let's come to a conclusion. We'll be drawing the line on this lesson with the understanding that vapor pressure and boiling points are key properties that describe how liquids behave when heated. So they depend on temperature and intermolecular force of attraction, and they are critical to practical and theoretical work in chemistry and fields that are related to chemistry. So that will be all for this lesson, and I'll be saying goodbye.